Hello everyone, this is Aditi Pal, final year student from AIIMS Nagpur, and now we are going to start organic compounds containing nitrogen part 2. Part 1 is already covered. So we talked about amines, their structure, their classification, their nomenclature, their preparation. So we saw the introduction, structure, classification, nomenclature, methods of preparation. Then we saw the physical properties and we had reached the chemical properties where we studied about alkylation and acylation. So now after completing this much, we'll move forward in the discussion of amines. So let's start. So first of all, the chemical reaction which we are going to study now is electrophilic substitution reactions. So like we studied in our haloalkenes and haloarenes, electrophilic substitution, similarly in aniline also, we see electrophilic substitution reaction. Why? Because we know that if we make the structure of aniline, we see that the nitrogen has a lone pair which will be involved in resonance. It will give its electron inside the ring and resonance structures will be formed. So aniline is ortho and para directing. So whatever are the electron donating groups, they are ortho and para directing towards electrophilic substitution reaction. This is the first thing that we have to remember, that they are ortho and para directing electron releasing groups or electron donating groups. So first comes the bromination reaction. So what do we have to remember? That aniline is there. What reagent will be given to us? Bromine in the presence of bromine, and water will be there. So what will the amines do? They will react with bromine, water, and since it is so much electron donating, ortho and para directing, that all the three positions, two ortho and one para position, will be substituted by bromine to form what? 2,4,6 tribromoprecipitate. So directly this can be given. They will give this, and they will ask that what is, suppose if this is A, so what is A? They'll ask like this in the question. So we should know that aniline is so much ortho and para directing that all the three positions are occupied by bromine to form 2,4,6 tribromoaniline. This is the first thing that we have to remember. Now moving forward, we see that bromination, we saw that only all the three positions were being occupied by bromine. Now, what if we want to do that? So, what will we do? We will first make this aniline react with CH3C double acetic anhydride. Okay, this can also come as AC2O. So we have to recognize what is this. AC2O can be written. So this is acetic anhydride. So what will happen? Acylation will happen. So here C double bond O CH3 will come to form acetanilide. Okay, now what? If acetanilide is there, now when we react with it, when we make it react with bromine in the presence of ethyl alcohol, then in the presence of ethanoic acid, then what happens? Then what will happen? Uh, now, since this group is ortho para directing, so now only one bromine will add on the para position. So, and when we react it with H plus or OH minus, then this group leaves and we get NH2. So because this will form salt, and so this will form again we'll get the NH2 group which we wanted in the product. So this will be the final product, and we see that no, like 2,4,6 tribromoaniline, like it was being formed in the previous reaction, that does not happen, because now we substituted aniline with our ethanamide group, this group that we call acetanilide. So this is not as much as ortho-para directing as aniline. So this results in the formation of 4-bromoaniline, and this is how we substituted only one bromine as like we wanted only one substituent. We did not want the product as 2, 4, 6. We did not want more than one substituent. So this is how we can proceed if we want only one substituent, and this they can give as an alternate reaction, like they can give we have this in the question, so when that question comes, I'll let you know. So the first was bromination, now we see nitration. Now nitration of aniline is not possible, okay, as it is susceptible to oxidation. So again, what we will do, since we cannot perform it on aniline directly, we will first convert it into acetanilide. Now the nitration of this acetanilide is possible, but the nitration of aniline was not possible. So we converted it into acetanilide. Now we will do the nitration, that is HNO3 in the presence of H2SO4. So now when we do nitration, then we see that NO2 group is able to attach at the para position or the para position. So, and then again, when we treat it with H plus and H2O, then this group leaves and NH2 aniline again comes back that we wanted. We wanted to do the nitration of anilines, but since we cannot directly do it, so we convert it first into acetanilide. So this is how we proceed in case of nitration, also similar to bromination. Like if we wanted to uh, attach bromine on an aniline group. Now we want to attach NO2 on aniline. So this is how we proceed. Now we move on to the next reaction, that is sulfonation. Now in this case, sulfonation of aniline is possible, and aniline on sulfonation, what does it give? It gives sulfonilic acid. So we have to remember that SO3H and NH2 group is called sulfonilic acid. So what will happen when this aniline will react with H2SO4, we'll do the sulfonation. Then first it will form NH3 plus and HSO4 minus. So it will donate its lone pair to the sulfur, and it will form NH3 plus and HSO4 minus, which is anilinium hydrogen sulfate. Now on heating it, this SO3H group will come here, and one H2O molecule will leave from here, minus H2O. So SO3H will come here, sulfonilic acid will be formed, and sometimes this H plus will leave from here and go here, since nitrogen has a lone pair and it will form Zwitter ion. So this is the Zwitter ion that can form. So this is the sulfonilic acid that will be formed on sulfonation of aniline. So we learned three reactions till now, that is bromination, nitration, and sulfonation. These two were not happening on their own. So in these two, we first converted aniline into acetanilide. That is a very important point to remember. And this happened directly. We did not have to convert acetanilide for uh, for sulfonation reaction. Now moving on, we come to the next chemical reaction in aniline, that is diazotization reaction. So what is this diazotization reaction? First of all, what is the diazonium salt? So Ar and 2x. So we this see this structure in which nitrogen has three triple bonds, and here X minus is there, and nitrogen has positive charge. We call it as aryl diazonium salt, and this part is called diazonium ion, that is N triple bond N and positive charge. These are the small things that we should know. This is known as diazonium ion. So we will call this as what? Benzene diazonium salt, because it has the diazonium ion. So this X minus can either be a Cl minus, chloride ion, SO4 2 minus. X minus can vary depending on whatever we use. But this part, that is N triple bond N and positive charge on N, is called diazonium ion. This is the first thing that we have to remember in case of diazotization, that what is diazonium ion. Now moving further, what happens in diazotization? So what is diazotization? So what do? We convert aromatic primary amine into diazonium salt. So this is aromatic primary amine. We do the reaction of this amine with NaNO2 in the presence of HX. X can be HCl. So Cl, Br. So we do in the presence of, uh, take it as Cl. So we do in 0 to 5 degrees Celsius. It can also be written in Kelvin. That means at a very low temperature, we convert this aromatic primary amine into aryl diazonium salt, and NaX and water is released. So this is the reaction. Now, now what will happen? We saw that aryl diazonium salt is formed. This is the structure of aryl diazonium salt. It can also be written like this. If it forms a bond with X, and so this triple bond gets broken. So these structures are interconvertible. Now we'll see an example that this is aromatic primary amine, that is aniline. Now we cause its reaction with NaNO2 and HCl at very low temperature. Then what happens? It forms this, which can be written like this, and it can be written like this. That means benzene diazonium chloride is formed. That is aryl diazonium salt is formed. So this process is known as diazotization. So first of all, we have to remember the structure of diazonium ion. Then what is the definition of this process? What is diazotization? That we have to remember. Now next comes what is the important part. What is the mechanism? So we had seen that we have NaNO2, and we have this in HCl. So this NaNO2 in the form of HCl, it will form HNO2, and more H plus ion is there. So what will happen, that this double bond can come, this um, H plus will attack on this oxygen, since it needs electron, and oxygen wants to give its electron more than nitrogen. So it comes and attacks here, and then water molecule comes out. So with this, see this, that we got this cation. Its name is also important. Uh, yeah, and this lone pair can be transferred here. So it will become nitrocilium ion. And this nitrocilium ion will now go and attack on the aryl primary aromatic amine. So this aryl group is there, and we have the amine group. So what happens, this lone pair will attack on, either it can remain like this, or it can form triple bond also. So they are both resonating structures. So it will attack here, since it has a positive charge. So after attacking here, this hydrogen will leave, and again it will the structure will be formed like this. Now what will happen, again H plus will attack, and this double bond will come here, and this will come here. So what do we get? We get diazo hydroxide, and again H plus will leave and H plus will attack. So H2O molecule will leave from here, and we finally get what we were looking for, that is aryl diazonium ion. These are interconvertible. So this is the diazonium ion that will be formed due to this diazotization reaction, where we are taking the reagents as NaNO2 and HCl at a very low temperature, that is 0 to 5 degrees Celsius. So this will be the diazonium ion that is formed, and it is they both are interconvertible structures. So if this triple bond comes here, then there will be a lone pair here, and if there will be a positive charge on this nitrogen. So these are interconvertible structures. Now, on moving forward, what are the important points in these reaction? That nitrosonium ion is attacking and it is carried out the primary rearrangement is possible wherever intermediate is a carbocation. So rearrangement is possible. Also, with secondary, this is very important to remember that with primary amine, diazonium salt is formed, but with secondary amine, yellow oily liquid of N-nitrosamine is formed. So this thing that is formed in case of secondary amines, it is a yellow oily liquid of N-nitrosamine. This is a very important point that we need to remember. Primary amines, everyone knows. So if they ask about what will happen in the case of secondary amine, a yellow oily liquid of N-nitrosamine is formed. Now we already saw what are diazonium salts. So 2-azo means nitrogen, am means cationic in nature. So 2 nitrogen and di means 2 nitrogen and they are cations, so they are called diazonium salts. We already saw that this is benzene diazonium chloride. What are diazonium salts? We have already seen. Now we have also seen the preparation. How do we prepare diazonium salts? Now what are the properties of diazonium salts? So these diazonium salts, they are ionic in nature. We already saw there is a cationic part and there is an anionic part. If they are ionic in nature, obviously they will be water soluble. Then these aryl diazoniums are colorless grains of we make secondary amines react in the in diazotization reaction, then yellow compounds. So, but that they are not diazonium salts, so to say. Then benzene diazonium chloride is soluble in water, but reacts only when it is warmed. So this benzene diazonium chloride, it will also be ionic since diazonium salts are ionic, so it is soluble in water. And benzene diazonium fluoroborate is not soluble in water. So benzene diazonium chloride or any diazonium salt will be soluble in water since they are ionic in nature. Cations and anions are present. But this thing, benzene diazonium fluoroborate, it is not soluble in water. It is not so important to remember. It is, but for the sake of information, it is given here. Now we move forward. We saw the properties. Now, why do we have to study about these diazonium salts? So they find application in the dye and pigment industries. So they will be used to produce dyed fabrics. Okay, due to their property of breaking down near reproduction. So they break down near ultraviolet light. Then they are also used in the synthesis of large variety of organic compounds, especially aryl derivatives. Okay, these diazonium salts are used for the synthesis of aryl derivatives, and then direct halogenation is not a suitable method for preparing aryl iodides and fluorides. Nucleophilic substitution of chlorine in chlorobenzene by a cyano group is not possible. Direct halogenation is not possible. Okay, so diazonium salts can easily be used to produce cyanobenzene. So they are saying that cyanobenzene cannot be formed easily. Like if you want to do nucleophilic substitution of chlorine in chlorobenzene, then we know that aryl halides do not give a nucleophilic substitution easily. So it is saying since it is not giving, so you cannot form cyanobenzene easily. But if you have this diazonium salt, then you can easily form cyanobenzene. It is not possible to prepare substituted aromatic compounds by direct substitution in benzene. And a similar thing is written that it is not possible for us to produce substituted aromatic compounds by direct substitution. We cannot substitute directly, we have to use an alternate method. So instead of using that alternate method, we can use diazonium salts if we want to um, substitute any of the groups in benzene. They are used as intermediates for introducing F, Br, Cl, I, NO2, OH, and CN groups into the aromatic ring. Okay, these to substitute a benzene with any substituent, then it is not easy for us to do that. And in that case, we will be using diazonium salts as an alternative method. Okay, so now creation of diazonium salts. Now we have to see reaction with nitrosyl chloride. So this nitrosyl chloride NOCl is also called Tilden's reagent. So they can use this word Tilden's reagent. So and when then it forms alkyl halide and N2 gas is released and water is released. Okay, so we have to remember this. What is Tilden's reagent? So Tilden's reagent is NOCl. We have to remember this. And what are the products of this reaction? Alkyl halide and N2 gas is released and H2O is released. So this is how the products are being formed. So first diazonium salt is formed, and after that alkyl chloride is formed. This also we have to remember. Then only N2 gas can leave from here and RCl can form and leave from here as water. C is. So what do we have to find? C. Okay. Here we saw that NH2 and CH3 is there, and NaNO2 in the presence of HCl 0 to 5 degrees Celsius. Okay, now only we saw what will happen in this reaction. This is our diazotization reaction. So diazonium salt will form. The first step is clear. Now we did not see this till now. So what is this? So this is Sandmeyer and Gattermann reaction, that is replacement of diazonium group. So diazonium, till diazonium we reached. Now if we make it react through these reagents, then what happens? This diazonium group is goes out, like replaced by what? Cu in the presence of HBr, then Br will come. CuCl in the presence of heat, Cl will come. CuBr in the presence of heat, again Br will come. Cu copper in the presence of HCl, then Cl will come. So we see, if we use HBr and HCl and copper in the presence of HCl and HBr, then Br and Cl respectively is coming, while in case of CuCl and CuBr, Cl is coming and Br is coming. Okay, so replacement of diazonium group by chlorine and bromine to form chlorobenzene and bromobenzene is called Sandmeyer and Gattermann reaction. So our first part was clear. We read the formation of diazonium salt. We prepared the diazonium salt. That is given in the question. Okay. So first part is clear. Second part is also clear, that chlorine will come here. Now the compound form will look something like this. Okay. Now we have we have to react it with Cl2 in the presence of uh, Cl2 in the presence of H nu. So what happens here? Free radical substitution will occur. So CH2Cl will form. So this is now uh, our product. Till here we reached. Now finally we react it with Na plus in the presence of dry ether. This is Woods reaction. We have read it in alkanes. So this is Woods reaction, and here we know, since this thing will move out. Okay, so this thing will move out from both, and here two molecules of this will react to form this dimer. So if we see the options, then which is correct? So we needed to know three reactions for this particular question, not three, four reactions. First is this, that is diazonium salt preparation. Then they also want us to know of Sandmeyer and Gattermann. Then they also want to know that if then we have studied alkanes, alkanes give free radical substitution. So this is a free radical substitution. And finally, they want us to know about Wood's reaction also. So this is a check of our complete knowledge, and this is the answer for this question. So now we move on. This is a Sandmeyer and Gattermann reaction. So now we move on to the next question. This is the major product Z obtained in the following reaction scheme is. So this is what, and we are reacting it with NaNO2 in the presence of HCl. See, they have given temperature in Kelvin, that is 0 to 5 degrees Celsius only they have written. So this is what, again, diazonium salt will be formed. So here we will get N2 plus and Br minus. Okay. Now Cu2 Br2. So they want us to replace this with Br only. So Br is here and Br is here. Okay. Now what? Now they want us to do nitration. Now what will happen? This bromine is ortho and para directing. So this bromine is also ortho and para directing. So in both cases, if we consider, if nitrogen group won't come at this position, so why won't it come at this position? Already one bromine and one bromine is there. There is no space for it to come. There is a lot of steric hindrance. So this is wrong. And two nitrogen also won't attach. So, and the position of bromine, it will come at para position. With respect to this bromine, it is ortho. With respect to this bromine, it is para. So this is the most favorable position for nitrogen to come and attack. So this B will be the correct answer for this question. So this is the correct answer. And now we move on to the next. So first diazonium salt was formed, we saw. Then diazonium again Sandmeyer and Gattermann. So it was replaced by Br. Now we want either it can attach at this position because this is ortho with respect to this and para with respect to this, or ortho with respect to this and para with respect to this. This was not in the option, so this is correct. Now we have to two diazonium salts. Now we move further. So in the following reaction sequence, we have this NH2 and we have CH3. I just told you that they will give AC2O, that is acetic anhydride. So A will be formed, will be acetanilide. Okay, acetanilide will be formed. Now what will happen? So when 4-methyl aniline will react with acetic anhydride, it will form acetanilide. Okay. Now this acetanilide group is more electron donating than methyl group. Yes, it's more electron donating. That will plus M effect, and plus M effect, and it will back at ortho position. So we know that plus M effect whenever it is there, ortho and para position, para pe already CH3 is there, so we cannot attach bond O. CH3 will be there and bromine will be there with respect to it at the ortho position. So this will be our correct answer. And we saw how it will happen. So AC2O, first it will form acetanilide. We are seeing here acetanilide is being formed, and further on reaction with bromine in acetic anhydride in ACOH, it will form ortho directing bromine will attach. So this is the correct option. Now further, the increasing order of diazotization of the following compounds. Now we have to arrange in the order of diazotization. So we know that we have to know one thing for solving this question, that aryl diazonium salts are more stable than aliphatic diazonium salts. So aryl diazonium salts here will be more stable than aliphatic diazonium salts. Okay, so A will be the least, since A is an aliphatic diazonium salt will be formed. So A will be the least. So option A cannot be the answer. Now in case of C, D, and B, this is pure aniline. Here aniline, and it will be at the meta position. We have this group, and here we have ortho position. We have C double bond O CH3. So what will happen, since it is at meta position, so it will act as electron withdrawing group. Okay, and electron withdrawing group is present. So what will happen, that because electron have here diamonds positive charge, so at meta position and electron withdrawing positive makes it more stable. More stable, and in both cases we have electron withdrawing group, so they are going to come in between. B will be the most susceptible for diazotization, and A will be the least. We know that this much. Now in case of C and D, since C has meta directing at meta directing position, and that will make it more stable. So after B, C will come in the order, and then D, and then finally A. So this will be the correct answer for this question. Now moving on to the next question. P on reacting with NaNO2 and HCl at 0 to 5 degrees Celsius, and then reacting with beta naphthol in the presence of NaOH, forms a color solid, while P with reacting with bromine forms Br3. Now, what will happen? Br3 is forming, we just now saw 2,4,6 tribroaniline. It happens when there is so much ortho and para directing. So ortho and para directing means here bromine should be attached. So here already CH3 is there, it cannot be the answer. Here also already CH3 is there, and it is not aniline only. So these three are already cancelled. So this is obviously the answer. But we will see what happens when this thing reacts with NaNO2, HCl, and then beta naphthol. So this logic we saw that they cannot be the answers, and we already got the answer. But if this thing reacts, then we will get diazonium salt. Okay, but when this reacts with beta naphthol, then colored compound is formed, and this is the colored compound. So this we should know. So we knew this, and we saw it according to this. But we should know what happens when this diazonium salt base, then it will form azo dye, that is a colored compound. So this is formed beta naphthol, and azo dye is formed. So this also we should know for our knowledge, that diazonium salt reacts with beta naphthol in dilute base to form an azo dye, which is a colored compound, which can be asked in questions. So this was the question. Now we come to another reaction. That is the Hinsberg reaction. Now what happens in Hinsberg reaction? So Hinsberg reaction is reaction with benzene sulfonyl chloride. Okay, so first of all, Hinsberg reaction, they'll ask what is the reagent, then that is benzene sulfonyl chloride. This is the structure. It is called Hinsberg reagent. The reaction with benzene sulfonyl primary amine. This is our primary amine to yield what? N benzene sulfonyl amide. So here HCl moves out and N-ethyl benzene sulfonyl amide is formed. If this is a case of primary amine. Now, secondary amine can also react with benzene sulfonyl chloride, but tertiary amine does not react with benzene sulfonyl chloride. What we have to remember that this benzene sulfonyl chloride or Hinsberg reaction is used to distinguish primary, secondary, and tertiary amines. This is the main thing that we need to remember, that this is a reaction which is used to distinguish primary, secondary, and tertiary amines. So primary will react, secondary will react, tertiary will not react. Okay, this much we understood. Now what happens? We have this benzene sulfonyl chloride. It has L negative this is primary amine goes and adjusts there. Okay, double bonds there. That is formed. That is all. And then what happens when we dissolve it in aqueous NaOH or KOH? Then what happens? Then H plus will move out from here and it will form a salt. And since it becomes in the form of ions, that means it is soluble in this aqueous NaOH and aqueous KOH. Whenever it becomes in the form of ions, that means it is soluble. Okay, this will happen when it has one H. Now, secondary amine will not have any H because here, since from here, already the H will be removed. So it will not form ion and it is not soluble in case of secondary amine. So in case of secondary amine, it will not be soluble in aqueous KOH and aqueous NaOH. So we already differentiated, means if we use benzene sulfonyl chloride, if they react, then we already know either it is primary or secondary amine. And if it does not react, it is tertiary amine. Now, how will we differentiate this primary and secondary amine? Then we will differentiate it by dissolving in aqueous NaOH and aqueous KOH. If they dissolve, then they are primary. If they do not, then they are secondary. That's how we distinguished all the three types of amines. So this is the importance of this reaction. Now, this we saw primary amines, what they will form: N-alkyl benzene sulfonamide, which will form PPT. Secondary amines will also form PPT, but in aqueous NaOH, this PPT will dissolve. Why? We saw that one H plus ion will go, but here there is no H plus ion. How can it react with OH minus ion to form a salt? So this is not going to dissolve. PPT won't dissolve. So we are able to differentiate primary and secondary amines. And tertiary amines, we already know they do not even react with benzene sulfonyl chloride. So they will be excluded at first only. So to distinguish them, what did we use? We use aqueous NaOH and aqueous KOH and dissolve them in it. So this is how we distinguish between the three types of amines. Now we move on to the next topic, that is Beckmann rearrangement. Now, what is this Beckmann rearrangement? It is acid catalyzed conversion of keto oximes to amides. So what do we do? Acid catalysis is there, acid is used, and we convert keto oximes and we convert these keto oximes to amides, and this is known as Beckmann's rearrangement. So we'll see that how it happens. So we will use an acidic medium, so we can use concentrated HCl, concentrated H2SO4, or we can use these Lewis acids. So whenever in paper they can give you Lewis acids also. Acid is there, so they can give anything. So first what will be formed? First oxime will be formed and then amide will be formed. So we have to remember this rearrangement, that what happens. So we have to identify the Beckmann rearrangement in our exams in the past. the questions. That is what the examiner wants from us. So what happens in the reaction mechanism? Firstly, the formation of oximes occurs. So what happens? This is a ketone. We have NH2OH. It goes and attacks, and this O gets negative charge. Then what happens? Elimination of OH minus happens, and then what happens? Deprotonation happens, and H plus and OH minus gets removed, and finally double bond N and OH is formed, which is an oxime. So oxime gets formed and H2O is released. Okay, so this is the first step. Now what happens? Now rearrangement takes place and alkyl migration occurs. So what will happen? Alkyl migration will occur. That means this is going to attach here, and now the six-membered ring becomes a seven-membered ring with nitrogen inside. And this OH2, it gets removed from here and then it again attacks. And so that SO3H can also attack, and then protonation, that is tautomerization, occurs, and finally this double bond NOH is converted into amide. So we saw this rearrangement occurs, tautomerization occurs, so that an SO3H will get removed with H plus ion here to form finally amide, and rearrangement has also taken place. So this is Beckmann's rearrangement that we have to identify with the help of reagent, that oxime is forming and then amide is forming. They want why we don't have to get reaction. We Beckman about so amides are basic. So we said that bonds pair, so they will react to form a salt. For example, NH2 has lone pair HX, in which case H plus and X minus is there. They will react to form RNH3 plus, that is salt. Similarly, aniline will react with HCl to form anilinium chloride. So aniline is base. We know that amines are basic, and aniline is also basic. It has a lone pair which it wants to donate to whatever Lewis acid is there. So basicity, we know that they are basic. Now basic character, we used to take out in when we studied equilibrium chapter, Kb value. What will be the Kb value? When amine reacts with water, it forms RNH3 plus OH minus. So what is the Kb value? Kb value can be written as this, like this. We have already studied in equilibrium chapter, and since H2O is a can be ignored. So this is the final expression for Kb. And we also know, we have to know that Pkb is equal to minus log Kb. So Kb is inversely proportional to Pkb. Kb is the order of basic strength, and it is inversely proportional to Pkb. So in questions, for solving questions, we need to remember this relation. Okay. Now, so if Kb is large, then pKb will be less. Like that, we are able to understand that that will happen. Now, basicity of amines. So if we compare alkanamines versus ammonia, which is more basic? This is ammonia, this is alkanamine, and this is ammonia. Now, if we try to understand, this R group will be CH3, C2H5, anything like that. So they have electron releasing tendency, while hydrogen will not release electron. So they will have electron releasing tendency. So electrons are more available in case of alkanamines rather than ammonia. So electrons are more available, so they are better bases than ammonia. This is the first thing that we have to remember. Alkanamines are better than ammonia. Now, if we want to see aryl amines versus ammonia, then we know that in aryl amine there is a lone pair, but it is involved in resonance with the ring, and it is increasing electron density at ortho and para position. So we know this resonating structures, ortho and para position, electron density is increasing. So if electrons are busy in resonance, that means they are not localized at one place. If they are not localized, how can they give the electrons? Electrons are always moving in resonance, so it is hard to give electron. So it means that they are less basic than that of ammonia. So they are less basic than ammonia. Whatever aryl amines will be there, they will be not as basic as ammonia because their electron pairs are busy in resonance. They are not available for donation. So this is what we understood. Now, how will we determine the basic strength? So we have to look at some things orderly. So first of all, we have to see that electron pair is localized or delocalized. So if electron pairs are localized, then they are more basic than delocalized. This is the first thing that we have to see. If we already saw this and we are not able to determine which is a better base, then what will we do? We will add H plus to make it a conjugate acid. And then we will see if our conjugate acid is resonance stabilized, or is it whose conjugate acid is more stable. So whosever's conjugate acid is more stable, they will be a better base. Then we will see hybridization of conjugate acid. So this is the conjugate acid. Even if we failed here also, we are not able to determine which is a better base, then we will move to our uh, third process, that is hybridization. We will see if um, hybridization of the conjugate acid, which has, like, if nitrogen is forming 5 bonds, then it is not possible only. So hybridization of conjugate acid, we will see. If we fail at this step also, then the final is solvation method. What is the solvation method? We know that nitrogen has 3 hydrogen, and if it dissolves in water, the oxygen atoms, uh, just NH4 plus if we take, then oxygen atoms will surround it. This is the solvation process of solvation. And more the amount of solvation, less will be the more is the solvation energy released, and less. So more energy released means more stability. So they will be more stable. But in case of, if we replace hydrogen by alkyl groups, then the solvation will decrease. That means stability will also decrease. So this is how we will determine in cases of solvation. So these are the 4 steps that we have to follow in case of determining the basic strength. So we will solve some. And one more thing we have to remember, that if we consider the gaseous phase, then we know that since they are electron donating groups, so this is the most basic, then comes 2, and then comes 1, and then finally comes our ammonia. But if we see the aqueous phase, now only we studied that ammonia has the highest solvation. So in case of aqueous, it becomes opposite. On combining these both two, what order do we get? So if this ever comes in exam, these orders we are supposed to know that 2 is greater than 1. That means 2-degree amine is greater than primary, is greater than 3 degrees, greater than ammonia. So this we need to remember. Like, this is some orders we determine by our own, and some orders are already determined, so we need to know them. So this is the order that we need to know, we need to remember. So now we can solve some questions. Increasing order of pkb. Again, pkb is inversely proportional to basic strength. So first of all, we will arrange them in the order of their basic strengths. So here we see 2 methyl are there, 2 methyl are there, 1 methyl is there, 1 methyl. 1 and 2 will be greater than 3 and 4. This I already know, isn't it? So 1 and 2 will be greater than 3 and 4. Now in case of 1 and 2, this is also giving its electron. That means 1 is more than 2. This much, 1 is more than 2, I already solved in terms of basic strength. So opposite is 2 is greater than 1. So these two options are gone. Now, if I see in case of 3 and 4, so here these groups are same, and now meta position means minus I effect. Cn has much more minus I effect than OH. So this becomes the least basic, means in case of pKb it will come at the first position. So option B is the correct answer. Now moving on to the next question. The increasing order of basicity of the following compounds. So first, what did we have to see? We have to see localized and delocalized. Here electrons are localized. Here electrons are delocalized. Here they are localized, and here also delocalized. So A and C will be greater than B and D. That we know. So increasing order of basicity. So our C will be greater than C and A will be greater than B and D. Now what should we have two nitrogen atoms here, sorry to say, two nitrogen atoms. One is involved in resonance and the other is free. That means it is also localized. So our B will be the least. That we know because it has delocalized and rest all are localized. So B is the last. So these two options are gone. Now what do we have to see? That here the atoms are more easy to donate and it is so C will be the highest. Then we come to D and finally we come to E. So B will be the correct answer. Now moving on to the next question. The decreasing order of basicity of the following amines. Again, see for delocalized and localized electrons. So here electrons are delocalized. Here the electrons are localized. Here also they are localized and here they are delocalized. So B and C will be greater than D and A. Okay. Now what? Now among localized electrons, C will be greater. We saw in the previous question also. Getting electrons from inside the ring is much easier than getting electrons from outside. Then among D and A, which is a better base. So this aniline will be a better base than this NH plus. How we will see by the second step was we will make it a conjugate acid. So here we'll make positive charge. So this positive charge, since this positive charge will be more stabilized by resonance, more resonating structures as compared to this positive charge. So C, B, A, and D is the correct answer. Now, in the following compound, the favorable sites for protonation. So A, B, C, D, E, which can be protonated means which are, they want to ask which are basic. Basically, they want to ask. So this thing is involved in resonance. We are seeing pi sigma lone pair. So this is involved in resonance. This can't be the answer. So E option is gone. Now here A is also involved in resonance. A is gone. So all the options are cancelled out. It means B is the correct answer. They are favorable sites for protonation. Now we have to arrange the following amines in the decreasing order of basicity. So again, first of all, 3 is the greatest. I can see and tell cause it is easier to get electrons from here than from here. And these are involved in resonance. So it is the last. So 3 is greater than 1 is greater than 2 is the decreasing order of basicity. Now again we have to arrange in the order of increasing order of basicity. So we have to find out. So first of all, here we see 3 methyl groups most donating. Here it is involved in resonance. So so uh, which will be the first? So C is the most basic in here. Then comes D, then comes B, and then finally the least is A. So this will be the correct answer. Here CH3 group is also there. That's why it becomes more acidic than A and B. So this is the correct answer. Now increasing order of pKb for the following compounds. Again pKb. So first we have to arrange them in the order of basic strength. So order of basic strength, B has here the electrons are involved in resonance and here also electrons are involved in resonance. So what we have to see, that the resonating structure of B, both nitrogen are involved in resonance, whereas in this case, only one nitrogen is involved in resonance. So increasing order of basicity will be uh, B is greater than C is greater than B is greater than A is greater than C. So the order of basic strength will be C. KB will be inversely proportional to PKB will be inversely proportional to KB. So order will be C is greater than A is greater than B. That's all for organic compounds containing nitrogen or amines. I hope all of you understood it, and keep solving questions, and all the best. Thank you.